Hello, I'm Riccardo Marchesin from the University of Trento, and in this talk I will present you a paper written together with Massimo Bartoletti and Roberto Zunino on DeFi composability as MEV non-interference. So first let's start from the context of our work, which is that of decentralized finance. And in a DeFi ecosystem, we have some complex financial services that are constructed by combining smaller smart contracts. And in such a scenario, we need to consider the fact that the security of the whole system is something more than the security of each component. And this is because the interaction, the dependencies may introduce some vulnerabilities that can be exploited by a malicious user. In this work, we focus on economic attacks, so we disregard bugs in the programming language of smart contract or problems with the cryptography of the blockchain, to look at the economic incentives of contracts, and in particular we will talk about MEV attacks, which are maximal extractable values attacks, and essentially they tell you how much can one gain from a certain state of the blockchain. When talking about composability, we are essentially asking the question, does a set of contract delta interact safely with the rest of the blockchain? And the blockchain S in this notation. And we argue that you can look at this question from two different points of view. The first one is the epsilon composability found in the literature in the Clockwork Finance paper that regards the contract as safe if they do not significantly increase the extractable value of the whole blockchain. This is essentially the point of view of the adversary, because we are saying this contract is safe if the adversary cannot gain more than what he could already do in the state before the composition. One of our contributions is the definition of a local perspective that looks at the composability from the point of view of the contract. So essentially we will say that the contract delta is composable if the adversary is not able in the composed state to cause a greater loss to the contract than it was when looking at the contract in itself without the composition. And I will now provide some examples in order to clarify a bit the difference between the two approaches when looking at composability. So our examples are mainly based on a simple contract, which is the automated market maker, or AMM, that acts as an exchange between two types of token, T0 and T1, and algorithmically adjusts the rate of the exchange. For instance, we keep a simple rule within the example, which is that the AMM must have a constant product between the amounts of tokens of type T0 and of type T1 that are in its balance. And the incentive of this contract is for user to make it reflect the actual ratio of values between the tokens. So users are incentivized to provide the token that's worth less until the ratio of the token reflects their true value. In our examples, we will always consider tokens of same value for simplicity, for illustrating better the amounts that are in play without having to do some rate conversions. But we can look at how a user can extract value from an AMM. So this is a very simple example in which we have a blockchain with just a simple contract, and we see that an adversary, in this case, can which owns two tokens of type T0, can sell them in the contract because the AMM has a few tokens of type T0 and extract 6 tokens of type T1 from the contract. So essentially they are extracting value. This is not to be considered as a malicious operation, is in the intended spirit of the AMM, but we will see how we will still consider it as some form of MEV. And we can look now at the composition of two identical copies of this AMM to see what happens. Essentially, in the new state in which we are putting two copies of the AMM, The adversary can do something that's more clever, because they can divide their investment. They can spend 1 token in the first copy and gain 4 tokens of type T1, and then do the same in the second one, and so they can have a bigger gain, gain of 8 tokens of type T1 for the same loss, the same use of 2 tokens. So if you look at it like this, the composition from the adversarial perspective is not very safe. I mean, adding a new contract allows the adversary to extract more MEV. However, if I look at it from the point of view of this contract alone, which is being targeted by the adversary either in a state where it's only on its own or it's in the composition, well, the single AMM does not really care about being in a composition, because the new attack of the adversary actually extracts less from each of the copies. So we can see that from the perspective of the contract, this may be regarded as composable without problem, a situation in which the adversary doesn't really get some help from the other contracts, the second copy, in order to extract more from the first. And so the question is still open. Are these two contracts composable or not? It depends from which perspective are we looking. And now I will provide a slightly more interesting example in which there is maybe some malicious action, because we can consider a contract that is a bet on some exchange rate. So the contract price bet looks at a contract C, which is either an AMM or an exchange, where the rate of exchange between 2 tokens is set by an oracle, and allows some player to bet on whatever the exchange rate will be at a certain point in time. Now, these two different cases have different behavior with respect to composability, because if we look at the exchange, the price bet together with the exchange, well, then the rate is set by an oracle. So whoever is trying to win this bet cannot do much. If it's not the oracle, then they cannot cheat and change the rate in a way that's advantageous, that allows them to win the bet. However, if I'm betting on an AMM, I'm actually exposed to risk, because a malicious user can perform the bet, then cause volatility in the AMM to win the bet, and then simply return the tokens to the AMM to restore the balance, retrieve the amount of money that they use in this attack, together with the bet that they have won. So here, from the point of view of the contract price bet, the composition against an AMM might be considered as insecure, because there is some course of action that allows an adversary to exploit the rest of the context, the rest of the composition, to harm the contract, to maliciously win some bet that they should not have won. And so we have established this difference between the adversarial perspective and the contract perspective on composability, but we still need to give a definition. And here I will explore some possibility and present the one that we landed on in the paper. And the first solution for defining composability, which is unfortunately a bad solution, is to divide the state into part, and to say that some set of new contracts delta is composable with the previous part of the state S if the extractable value in the composed state is smaller than the sum of the two extractable value computed independently for contracts in S and contracts in delta. However, we have some problems, because this notion of MEV of delta is not well defined. For instance, if you look at the price bet contract, which has a dependency, and you are trying to understand if the price bet is composable with the previous state, so maybe the AMM or the exchange, well then, if you're trying to compute the MEV of only the price bet without putting the rest of the contract, then the functions are simply broken because they are not allowed to call the dependencies because the contract isn't there, because you have divided the state into different parts. You are trying to compute the extractable values in a state that does not include the shared dependency. And moreover, you are also not saying how to split wallets, because the adversary, as we've seen in the first example with the AMMs, may use wallets, their wealth to extract some MEV, and according to whether I put the wallets in one side or the other, it's going to be a different answer, and I'm often going to have some problems of double counting. For instance, if there is a shared dependency that has to be put both in S and in delta, then this is going to offer some extractable values in both parts. So this definition doesn't fully work, but it gives us something to look for. We want to look for the MEV of delta. We want to look for a local definition of MEV. In essence, we want to have something that tells us from which contract the value is extracted instead of looking at the whole blockchain. And such a definition has the potential bonus of simplifying the estimates of the extractable value, because it should allow us to look only at a part of the state of the blockchain instead of at the whole blockchain. And now we can go on to the full definitions. And I start with the definition of global MEV, which is what I've informally talked about up until now, just to introduce the notation. So this is the maximum possible gain of the adversary, so the tokens that the adversary can get by starting in a state S and performing a sequence of transactions that, and this is the tricky part, is craftable by the adversary. So it's can be produced with only the knowledge of the user, of the adversary. And so this is the global MEV. But if we want to give a definition of the local MEV, then we need to look at the loss of the contract, as I mentioned, as I anticipated earlier. So here we have the, as I said, local MEV of contract delta or a set of contract delta in a state S, and this is the maximal loss. So looking at the initial state, the loss between the balance of the contract in the initial state S and after a sequence of transaction X that are still transaction craftable with the adversary have been performed. And from this point of view, from the contract point of view, we are regarding as extracted value every token that exits the contract. Even if it doesn't end up in the adversary's pockets, it still counts as extracted value for the purpose of this definition. And essentially, we are modeling an irrational adversary that is doing its best to make the contract lose tokens. And together with this definition of local MEV, we have a companion definition, which is of restricted local MEV, which will be used to define our notion of composability. In the restricted local MEV, or MEV alone, we are trying to estimate the loss that the adversary can cause to delta without interacting with the rest of the blockchain. So the definition is very similar to the previous one, so it's the maximum loss starting from state S after a sequence of transaction X, but this transaction can only target delta, so they can only call methods of delta without without interfering, and that's where the non-interference part comes up, with the rest of the state. So we are finally there. We can give our definition of composability of non-interference. We say that given a state S and some new contracts delta, the contracts delta, the state does not interfere with the new contracts if the local MEV of delta in the new composed state is equal to the MEV alone, to the restricted local MEV of delta in the same state. And essentially, what this notion is telling us is that if these two extracted values are equal, then allowing or disallowing calls to a contract in S does not affect the MEV of delta. And essentially we can, even if we can achieve some extractable value by interacting both with delta and with the rest of the state, then we must be able to achieve the same value by only interacting with the contracts in delta, only calling the methods of this set of contracts that I'm considering. And we can now see an example of how to use this non-interference definition by looking again at the price bet contract. So we have a blockchain with maybe some adversary wallets, maybe some other stuff, but an AMM and a price bet contract that looks at the rate of the AMM and contains a balance of 100 token, and if somehow the rate of exchange is 3, then the participant wins these 100 tokens. This is, of course, a simplified example, but we can try to compute the two parts, the restricted MEV and the unrestricted local MEV of the contract price bet. So let's start first with the MEV alone, the restricted MEV. Well, here this is 0, because if an adversary is trying to target only the price bet without changing, without calling methods of the MEV, well, then they have no way of changing the rate, so they can not win the bet unless it happened to be already favorable to them. And on the other hand, if we look at the unrestricted local MEV, well, then the adversary can target the AMM in order to unbalance it and use this unbalance to create a rate of 3 and thus win the bet, take the prize, and then use the maybe spend some token to rebalance the AMM so that they did not spend too many money in the first part of the attack, in the unbalancing part of the attack. So we have a difference. We have that the restricted MEV is 0 because they have no way to actually win the bet in this state, and the unrestricted one is instead 100. So the two values are different, and the contracts are interfering. So there is not composability. We also have a more robust version of our notion of composability, which is the composability against rich adversaries. And this is useful because both our previous definition and also the epsilon composability that I mentioned as the adversarial perspective are dependent on the tokens that the adversary has in the current state. But in some attacks, the ones that use, for instance, flash loans, the adversary can have essentially as much tokens as he needs, provided that they are able to refund them afterwards. So we also consider a notion of a rich MEV, which is essentially the same as the previous one. We take the maximum possible local MEV of delta, where the state S is given by contracts gamma and wallets, and we are taking the maximum across wallets, essentially. So we have a local rich MEV of delta with respect to some contracts, some previous contracts gamma. And of course, we have a parallel notion of non-interference, which is that the unrestricted rich local MEV must be equal to the restricted one for two contracts to be composable. And finally, I can present some of the results that can be derived from our definition of composability, from our non-interference, or from our MEV non-interference notions. And first of all, we have some sufficient conditions that imply the non-interference between a set of contracts and the state. The simpler one is that 0 tokens in a contract imply non-interference. And this might seem just a sanity check, but actually there are some cases in which it's useful, because, for instance, you may want to define a new contract that compares some properties of other two and then routes the query towards the one that you deem better, and you can do so by constructing a contract that has no additional token. We have also some independence properties, and by that I mean independence with respect to contract calls, so no shared dependencies, and independence between input token and output tokens that are used to imply the non-interference for adversary with bounded wealth. So if you have a contract that a set of contracts that is fully independent between tokens and contract calls from the previous state, then you can also have non-interference. And an interesting thing is that for wealthy adversaries, we can drop the requirement on token independence. And essentially these, together with the fact that we can prove that the MEV of the MEV for rich adversaries can be computed by looking only at the dependencies of delta, these two properties tells us that there is something about this granularity of MEV that allows us to restrict the amount of contracts that we look into when we try to estimate the extractable value. And moreover, and this was already shown in passing with the examples, we have that our definition is neither implied nor it implies the epsilon composability definition, or the adversary perspective on composability. So there are some contracts that are composable according to one definition but not the other, and vice versa. And then we have investigated some preservation properties from non-interference. This is one of the tables from the paper. And so, for instance, we try to understand what happens when we are inserting more contracts in the state before checking the non-interference. And this is essentially akin to front running from the side of the adversary. So I'm trying to understand if in the current state I'm safe to deploy a contract delta, and well, I should be also safe if some new contracts are deployed between before I can append mine to the blockchain. And some other or also adding them to. We also checked what happens when we add contracts to the other side, to the ones that we are checking. There are also we checked also some property for removing contracts and some more complicated interactions. And finally, we investigated how some real-world contracts composition behave with respect to our definition of non-interference, and not only the AMMs that I mentioned up until now, but also lending pools and arbitrage contracts. To conclude my presentation, I just have this slide presenting some of the challenges that can be tackled as some future work on the composability of smart contracts in this non-interference framework.